Yes, cool. Okay, in that case, it's my pleasure to introduce the plenary talk of this international workshop. Today we're fortunate to have Professor Roland Duduchava from Tbilisi State University, who will give a talk on shell equations derived by the gamma convergence. So whenever you're ready.
Thank you. Thank you for the invitation. I will start with the definition of some calculus of tangential differential operators, which is a tool in this case to solve this problem of gamma convergence and the deriving shell equations with the gamma convergence. What is the main problem here? You have equation in some thin domain, and then we send this thickness of this domain to 0, and find we have Lamé equation in this thin domain, and would like to define in which sense we understand the limit of this process, and then derive the corresponding equation. And it should describe this thin shell problem. For this there are several problems. I will not list them. Well, we have some, as I told you, we have the domain, which is thin, and on the mid surface, we want to get the equation for this shell equation on the mid surface of this thin domain. And first of all, this calculus of tangential differential operators, which we call Günther's derivatives. Yes, here is this thin domain, omega h, which is some surface multiplied by minus h. Thickness is 2h, of course. And we consider the Lamé equation on this in this domain, in thin domain. And solution to this equation is well known. It is the displacement of this body under some load, displacement of the points. It's described by the vector u. Okay, and the boundary value problem, which we have in this case, is that the Lamé equation in the domain is equal to f. Then you have boundary conditions on the upper and lower surfaces, and on the lateral surface. On the lateral surface, we have the Dirichlet condition, but on the upper and lower surfaces, we have Neumann condition. So we're given with the traction operator, which is described here. The main question is what happens with the solution of boundary value problem when the h is sent to 0. For this, it is very convenient to apply gamma convergence and also calculus of Günther's tangential derivatives. I will start with the second one, then explain what is the gamma convergence, and then explain what equation we can get with such approach. Yes. Here we are. We have some surface, and we have this normal vector field to this surface in three-dimensional space, surface S, and the normal vector field is nu. The surface is given by some function, zeros of this function, which has a non-zero gradient, and the normal vector is given as the normalized gradient of this surface function. And so if the surface is given by such function, to find the normal vector field is quite an easy task. Okay, then we define the Günther's derivatives, which is not here, perhaps on the next slide. with the and this yeah, well, sorry. Actually, the Günther's derivatives is nothing more than the projection of the coordinate derivatives on this surface. It's not here, it will come later. I have no. And this normal vector field has the properties that the derivative, it's a gradient vector field. It's a gradient vector field. Here it is. Tangential derivatives, dg, is the coordinate derivatives subtracted the normal derivative multiplied by the appropriate component of the normal vector field. So it's, as I told you, it's projection of these coordinate derivatives dg on this surface. Okay, what advantages has this Günther's derivative? I will show you that they are very convenient to considering such problems, because it is first of all, it is a tangential operator and gives possibility to apply them to the functions which are defined only on this surface. Second, they are, of course, linearly dependent, and linear dependence is given here. Well, scalar product with the normal vector field is 0 because, of course, it is tangential vector. They are tangential vector fields, but they are full system. They are full system because any other first-order operator can be represented with the help of these Günther's derivatives. But surface gradient, defined in the differential geometry in a different way, it is just the gradient of these Günther's derivatives. They simply coincide. Oh, sorry, I jumped forward. And the divergence on the surface divergence is just the divergence with the written with the help of the Günther's derivatives. And the Laplace-Beltrami operator, which is in classical differential operator, classical differential geometry defined in the formula, which is here, it's just the sum of squares of Günther's derivatives. It's here. The Laplace-Beltrami operator is represented in such a simple form. Well, because it is combination of the divergence and gradient, as in the Euclidean space. Yes, it's written here. The Laplace-Beltrami operator is the sum of the squares of Günther's derivatives, although they are linearly dependent, and it is the superposition of divergence and gradient. Okay. The adjoint operator, you can calculate everything. Everything is okay, and this is the advantage which I wanted to show you of this Günther's derivatives. Well, sometimes we need to extend some this vector field, but it is done. Okay, let me skip this all definitions. Well. Here is here is formulated what I told you, that the gradient on the surface is the gradient of Günther's derivatives, and gradient and divergence on the surface is divergence defined by the with the help of Günther's derivatives. Okay, and traction operator written in terms of the Günther's derivatives has such a simple form, a lot of zeros there. It's a simplified form, and the Lamé operator is also written and can be written also in the terms of Günther's derivatives. Okay, now about gamma convergence. This was the tool. Another tool is the gamma convergence. What is the gamma convergence? When you have the some sequence of functions, the gamma limit is the following one. It satisfies the following conditions. The this well, any subsequence of this sequence is estimated from below by the lower limit, and there exists there is some kind of recovery sequence which gives you this lower limit estimation, this limit estimating from below this sequence. And this gamma convergence is totally different than the pointwise convergence. Here you can find it in the books, of course, but I listed here some properties and some examples when proving that the gamma convergence is totally different than the pointwise convergence. Sometimes we have gamma convergence and have not the pointwise convergence. Vice versa is also true. We have pointwise convergence, have no gamma convergence. And well, but the main also multiplication by -1 gives you sometimes non-converging. You have gamma convergence, but taking minus this sequence, the gamma convergence fails. But what is the advantage of gamma convergence? It is somehow very well adapted to the problems of mathematical physics. If you have sequence, or if you have the problem, what is the problem of mathematical physics? How they are solved? You find some energy functional, and find the minimum of this energy functional. This minimum of energy functional gives you the solution. And if you have sequence of such functions, the limit, if it is gamma limit, satisfies the same condition. It is infimum of the corresponding limit energy integral. So if you find gamma limit of energy functionals, the limit also will be energy functional, and you have the rigorous limit. Okay. Now, boundary value problem for the Lamé equation. I formulated the Lamé equation, boundary value problem for Lamé equation above, but let us repeat it. We have this thin domain, some surface, smooth surface, multiplied by minus HH. Is this around surface we have some body which has thickness 2H. And then we have this following boundary value problem there. Inside this thin domain, we have the Lamé equation with the right-hand side F. On the lateral surface of this thin domain, we have Dirichlet condition. If it is 0, it means that it is clamped, this surface. Not surface, but this thin domain. And on the upper and lower surfaces, we have this traction operator, which, if it is 0, means that the surfaces are free. If it is non-zero right-hand side, it means that it has some load. Okay. And now consider the, this is the Lamé equation, which we have in the domain. Lamé equation describes displacement of this body under some load. And we want to look now what happens when we send this thickness of this domain to 0. Okay. For this, we rewrite these equations in Günther's derivatives, and then after that we can send the thickness of this domain to 0. But first of all, rewrite it as a reformulate this problem in the terms of minimization of the functionals. Here we have the Lamé equation again, and we can reduce it to the problem when the right-hand side of the equation. Instead of f, we have 0, of course. That's we subtract some potential operators and get such an equation. And here is the energy functional, which gives you the following result, that the infimum of this energy functional gives you solution to this Lamé boundary value problem here of the 27. Problem 27 is equivalent reformulation is this one, that the infimum of this functional is the solution of the equation, and vice versa. Solution of the equation gives infimum to this boundary, to this energy functional. Now, reformulated the problem is the minimization of energy functional. We can apply gamma convergence, because now we have the sequence of functionals, and we can define for them the gamma limit. And gamma limit, to define gamma limit, well, what we do? Yes, here we have to mention that this problem for the plates, and with the classical of the coordinate derivatives, was solved by Friesike, James, and Müller in 2002. And they also have very short paper about when you have surfaces and thin domain, curved domain, but the technique is the classical differential geometry, and the results are formulated in a very different language. So it's totally different, how to say, in formulation. Of course, the result should be similar. And now we have this energy functional here, and we have reformulated our problem as the minimization of this energy functional, and now want to send our thickness of our domain to 0. Yes. To apply gamma convergence, we perform the scaling of the variable. Scaling of the variable means that instead of minus h, we will have the domain of thickness 2, minus 1, 1. Divide these variables by h, and then send h to 0. And the reformulation of our energy functional is written here. The scaled energy functional. Now, yes, here it's again explained what is the gradient and divergence, and because they are used here, everything is written in the terms of surface gradients and surface divergence. And the vectors, we rewrite it vectors, 3 vectors. Instead of 3 vectors, we have 4 vectors. We reformulated them because we have coordinate system, 3 tangent vectors, which are directional vectors for our Günther's derivatives, and the 4th vector is the normal vector. This 4-vector field is, of course, linearly dependent, but they are convenient to reformulate the problem for us. But we should be careful because it's linearly dependent, and not this representation is not always unique, but the condition which we impose gives well, how to say, it is unique representation. If we impose the condition on the last coordinate here, is the scalar product of nu of the remainder of the first 3 vectors. In this case, the representation is unique, and we apply this representation in our gamma limit. Okay, and now we have we introduce new variables and rewrite our equations, and well, minimize. Yes, now we are looking for the minimization of our problem. For this, we will get for these minimization problems, we will get these equations here and find out that the infimum of our sequence of energy functionals is this one. I mean, this is the lower estimate of the sequence of energy functionals when H is sent to 0. We have lower estimate. Now we have to prove that this lower estimate is also we have to find this lower estimate is the gamma limit. For this, we have to find to prove that this is the recovery sequence also. Recovery sequence. To prove that the gamma limit is we have a limit we have found is gamma limit, and this is also done. Recovery sequence is constructed explicitly and proved that it gives our limit. So the recovery, it is proved that the sequence which we found is recovery sequence. And what we now this we get, it's here, Q3, it's now the limit energy functional, which we get sending H to 0. Now what we will do with it, we will now reformulate it again as a boundary value problem, because there is a one-to-one correspondence between boundary value problems and the energy functionals. And the reformulation, of course, is not a very complicated task, and it gives this equation here. This is now the limit equation. We can consider it as a limit equation of the Lamé system. Limit equation of the Lamé system when H is sent to 0. And, well, one can now say that this limit equation is the equation for thin shell. Yes, let the weak limit in L2 exist. This is the conditions which we need that the gamma limit exists. These H's, I mean, these are functions which are given in the upper and lower surfaces. The difference divided by H should have a limit. And on the lateral surface, function which is given on the lateral surface should have also a limit when the thickness goes to 0. It's a natural conditions. And under these conditions, gamma limit of our energy functional is this functional, which I showed you, E3, which gives you this boundary value problem, which I also showed you. And here is reformulated now. We formulated the limited equation. Limit equation is this one here. And as you see here, it is something similar to the Lamé equation, but with lower order terms. And here also is present the mean curvatures. This HS is the mean curvature. It appeared here naturally, and in this equation on this surface, equation for shell equation on this surface, we have this limit. We have this condition. But what is interesting here, we had function on the upper and lower surfaces. You remember, that was the traction operator, had the boundary value problem was formulated, and the upper and lower surfaces, we had Neumann condition. And this Neumann conditions, upper and lower surfaces, they merge and the equation is now defined on this surface. And what happened with this our upper and lower surfaces conditions on the function on the upper and lower, given on the upper and lower surfaces? First of all, I remind you that this function here is the limit here is the limit of h on the upper surface minus h on the lower surface divided by 2h. And this limit function now appears in the right-hand side of the mean equation on this surface. So it migrated from the upper and lower surface condition. It migrated in the right-hand side of the equation, of the main equation of the shell equation, on the right-hand side of the shell equation. And on the lateral surface, we reformulated problem. It is again zero condition. It means that in this case, we have the clamped surface. But you always can reduce the problem, which is non-clamped, to the clamped problem by subtracting some known functions. So proof is based on the variation of the solution, that the minimum is this one. And well, it's conducted. Yes, about the solvability, we get this equation. We get the equation, limit equation for shells. And of course, it is interesting, the solvability of this equation. Is it solvable or not, what we get? Well, we look for unknown vector u1, u2, u3, which is linearly dependent, again, but it's solution of this equation 43. And does it has the unique solution? The operator is positive definite, what we get. The Lamy operator, which we had in the beginning, was positive definite, but the operator which we get as a limit equation, as a gamma limit equation, is also positive definite. And we can conclude that this problem will have a unique solution. Here is the proof of this, but I think I will skip the details of the proof because it is difficult now. Anyway, difficult to explain now the whole process of this proof. It makes no sense. And if the original equation is positive definite, that's a conclusion that the gamma limit is has a very good property that if the original equation is positive definite and we find the gamma limit of this equation, then the gamma limit is also positive definite, and it maintains the positive definiteness of equation. And this is very important. And this proof is also here. Yeah. Yeah, here is the uniqueness result. If the solution to the homogeneous shell equation vanishes on the boundary, it vanishes identically. So it's well, some kind, not some kind, but exactly the uniqueness of the problem. Uniqueness of the problem. Before going to this Lamy problem, to the shell problem, me and my colleague, Buchukuri, who is co-author of this paper, we also considered before that the heat equation. It means we have this thin domain and we have Laplace equation in this thin domain. And when we sent the thickness of the domain to 0, what was the limiting equation? It was much easier because it was a scalar equation, and we proved that the limiting equation was Laplace-Beltrami equation. Laplace-Beltrami equation. But in this case of this system, of course, it's slightly different now. because we had system, and system limit of the system, it's here, 42, equation 42. It's much more complicated. It's mu and lambda are the Lamé constants. D alpha, they are the Gunter's derivatives, but this H and the nu H are mean curvatures of the surface, and nu is the normal vector field. You see that the structure, the principal part of equation is like Lamé equation, but there appears a lot of lower order terms also in this case of system. Okay, when we have this scalar equation, the scalar boundary value problem for scalar equation, the limit equation is much simpler. But when you have system, the limit equation is much more complicated, and there appears curvature and so on. Curvature in the case of Lamé equation, of course. I don't know. We never considered other equations. Only Laplace equation in thin domain, and the Lamé equation also in thin domain. Thank you for your attention, and I am ready to answer your questions if you have some.
Lovely, thank you very much. So, are there any questions? So I was going to ask. I was actually going to ask about the heat equation on the thin domain, and what would happen if have you considered any different types of boundary conditions instead of Neumann boundary conditions?
Oh,
i.e. Robin or Duduchava?
I have to say, why we choose this condition? This is the natural formulation for these shell problems. I mean, the free surfaces, upper and lower surfaces free, but we put also function there if there is some load, and the clamped lateral surface. Of course, it is possible to consider other kind of boundary conditions. For example, on the lateral condition, you can choose also Neumann conditions. And I think there will not be big problems to find the gamma limit also, but we never tried. If there will be some, say, interest in such problems, of course it can be done, but it can be done by other people also. No problem.
Thank you.
We are how to say, following the principle that the problem should be interesting in application to formulate and solve it. When you are considering such equations as Lamé equations, everything should be more or less natural, you know.
Yes,
it should correspond to the needs what engineers have.
Yes. Thank you very much. So any other questions? Okay, well, in that case, thank you very much for the talk.
Thank you.
And
thank you.
Now we'll have a short break until 4 o'clock in Central European time, and where we'll have a talk by Brian Grajales.
Okay.
Thank you.
Thank you.